Hey everyone, this is going to be lesson number 10 for abstract algebra. Today we're going to give proofs for the second and third Sylow theorems. I will not provide any good examples for using them because I'm going to dedicate a whole video to that, which should hopefully be lesson number 11, which should practice using the first, second, and third Sylow theorems all together. Since it's a really important subject and takes a lot of different examples to really get the hang of these theorems because they're kind of hard to memorize at first. So last time we proved the existence of p-Sylow subgroups. So we proved the existence of p-Sylow subgroups. You can kind of imagine that this step, the first Sylow theorem, is kind of getting our footing for Sylow subgroups. You kind of have to prove they exist before you prove anything more interesting about them. Because, well, if they don't exist, then what's the point of really studying them? So the second and third theorems are more dedicated to proving properties. So second and third theorems are dedicated to proving properties about Sylow subgroups. About Sylow subgroups. Sometimes I will abbreviate subgroups as just sub-GPS. Okay. So hopefully this should give you a kind of good idea of why we would want to prove these things, because it's not just helpful to have an understanding that they exist, but we want to have a good understanding of what we can do with them. So the second theorem, just to give a quick overview of what each of them is going to do for us, the second theorem is going to tell us that all p-Sylow subgroups are conjugate, and I'll explain what that means. Are conjugate to one another. And this will give us the realization that they are all isomorphic to one another. This means if you give me any two p-Sylow subgroups in a group, I can prove they're isomorphic to one another. And the third theorem is going to tell us how many of them there are. So it basically lets us determine how many Sylow subgroups there are, p-Sylow subgroups there are. And we'll also discuss why that's something that's worth studying. The question of how many there are, because it'll help us learn more facts about how the p-Sylow subgroups have some kind of structure within the larger group. So okay, let's write out the second theorem rigorously and we'll prove it. Okay. Sylow second. So how it's going to start is you're going to let P and Q be two different p-Sylow subgroups in G. Be p-Sylow subgroups. Then we get there exists an element G in G, so G in G, such that Q equals G times P times G inverse. And so this is what I mean by conjugate. Hopefully you remember the conjugate operation that we've discussed before, which is taking a group element and then multiplying it by GH inverse. So G and G inverse on either side. And so this is then extending that to subgroups. So take one subgroup and find this set, which is G times P times G inverse. So I should note GPG inverse is the set which is G times little p times G inverse for all P and P. So in a sense, we want to prove that when you take one Sylow subgroup and you conjugate it by some element, you're going to get another. And we want to prove that if you give me any two subgroups, p-Sylow subgroups, there is some element which makes one the conjugate of the other. Okay, so let's prove that. And then we'll discuss why this implies that they're all isomorphic. So just to get started, you should first check for yourself that when you conjugate by some element of a p-Sylow subgroup, you get another p-Sylow subgroup. First check that this map, which I'm going to call phi sub g, which sends p to gpg inverse, is a bijection. And you should check this for all g and g. So it should be true for any group element. So this just verifies that this theorem even makes sense. That if you take a group element and you conjugate a p-Sylow subgroup by it, you're going to get another p-Sylow subgroup. Okay. So just to get some intuition for how we might approach this proof, we're looking for when q equals gp g inverse. Well, this implies if I multiply on the right by q, by g, I get qg equals gp. And now I'm going to do something, which is I'm going to cleverly multiply on the right by the set p. So I'm going to just imagine multiplying by the set p. And having two p's, this is just the same as one p. If you multiply any two group elements together in a subgroup, you're just going to get the subgroup again. So I'm looking for something that kind of looks like this. In that if I take, hopefully you should notice that I'm kind of looking at left cosets here. I have a GP here and a GP here. So I'm looking for some element G where if I look at the left coset of P with respect to G, Q does nothing to it. In that if I multiply Q by this left coset, I get the left coset back. So hopefully this should remind you of maybe a group action. In that maybe there's some kind of group action where Q acts on the set of left cosets, which is G mod P. So this is the set of left cosets, which lets us get this. Q comes from this group action. And if Q acting on this does nothing, then we're looking for the fixed points of this group action. So something where Q doesn't do anything to it. So hopefully all of those facts should give you an intuition for how the proof is going to work. Okay. Let's start the real proof now. So let's let Q, as we said before, act on G mod P by H dotted with some left coset is going to be equal to H times G and that left coset. So you should check for yourself that this is indeed a group action. So verify that this is a group action. Shouldn't be too hard. And we should note that as we've defined it, we would like to find fixed points. So let's describe like what those fixed points are. Fixed points. So the fixed points are going to be some kind of element, some left coset, such that the stabilizer of this is the entire Sylow subgroup Q, which can also be interpreted as QGP equals GP, which is exactly what we want. So in a sense, what we're looking for is to prove that there is a fixed point. If we can prove there's a fixed point, we can prove the entire theorem. Okay. But since we cleverly chose Q to be the group that's acting on the set, Q is a P group, which means we can apply the P group fixed point theorem. So let's apply P group fixed point theorem. P group fixed point theorem. And what we find is that the fixed points of our set G mod P, according to Q, is equivalent to just the size of G mod P mod R prime P. Okay, but you should remember that we've defined G to be of order P to the N times M, where P doesn't divide M. So like this P to the N is the largest power of P that goes into G, which means the size of G mod P is going to be equal to the size of G over the size of P, and the size of this p-Sylow subgroup P is just P to the N, so I get M here. And since P doesn't divide M, this means that this is not equal to 0 mod P. But if you remember when we were discussing the P group fixed point theorem, this immediately implies that there exists some element GP in the fixed points. Because if there wasn't, then this would be 0 mod P. But since it's not 0 mod P, it's guaranteed to not be. There has to be some element in here. Okay, this is great. Okay, so now using this, we can say there exists some element G in G. This is starting to seem like what we want, such that for all H in Q, I get that this H is going to fix my left coset. So I get that H dotted with, so this is the group action GP, is going to equal GP, which implies that HGP equals GP. And now I can say that this implies that there exists some elements P1 and P2 in P, such that HGP1 equals GP2. And now finally, I can just try to solve for H here. So I get that H equals GP2 times P1 inverse times G inverse. But if you see, this is exactly an element of the set G, P, G inverse, because I have a G on the left, some element of P here, so this is the G, this is in P, and this is G inverse. So this tells me for all H and Q, H is in GPG inverse, which just implies that Q is a subgroup of GPG inverse. Okay, that's great. But really the question is it the entire group? That's what we're trying to prove, not just that it's a subgroup. But if you remember, the size of GPG inverse, if you checked yourself that it was a bijection to P, has to be P to the N, which is also the size of Q, since they're both p-Sylow subgroups. So if one is a subgroup of the other and they're the same size, that means they have to be equal to each other. And that gives us exactly what we wanted to prove. Okay, so let's look at some quick corollaries of this theorem. So the first corollary, which I discussed, is that P is isomorphic to Q. And the proof of this, as you can probably see, is if I define some map psi, which goes from P to Q, and sends psi of P to GPG inverse, where G is that element such that GPG inverse equals Q, then I get that psi is an isomorphism. And hopefully you can check this for yourself. Okay. Another corollary, which I think is a good way of thinking about Sylow's second theorem, is if we imagine the action of G acting on our set of Sylow subgroups for the prime number P by this action, which hopefully you can guess now, which is G dotted with a p-Sylow subgroup P is going to be GPG inverse, then this action is what's called transitive. this action is transitive. This implies, if I haven't discussed what transitive means yet, or you're not sure, transitive means that there's only one orbit. Only one orbit. There's many ways of defining it, but this is kind of the easiest way to understand it. Which just means if I look at the orbit of P, is going to equal the entire set. And this is clear just from the second Sylow theorem, because let's say you want to say if Q is in the orbit, where Q is another p-Sylow subgroup, well, I know there exists a G such that GPG inverse equals Q, which means Q has to be in the orbit of P. Okay. And this is this corollary is gonna help us prove the third Sylow theorem. So recall that the third Sylow theorem is going to be about calculating the size, or should I say how many p-Sylow subgroups there are. Third Sylow. It's going to be about the size of this SP of G. So this one claims that, and note, NP equals the size of SP of G. This is going to claim that NP is equivalent to 1 mod P, and we're going to actually be able to completely determine what it is. It's going to be the index of the normalizer of P in G. And note this is just equal to the size of G divided by the size of the normalizer. And this is where P is any p-Sylow subgroup. Is some p-Sylow subgroup. Okay, let's try to prove this. So we're first going to prove that NP is equivalent to 1 mod P. So hopefully just like the way that looks, which is the size of SP of G is equivalent to 1 mod P, just the way this statement looks should remind you of the P group fixed point theorem. So that's exactly what we're going to try to use. So let's let our P group P act on the set SP of G. And the way it's going to act on it is, how you might expect, is G dot in set S is going to be GS G inverse. Okay, this comes up a ton in these proofs, the conjugate action. So G is some element in our P group P, and S is some Sylow subgroup in SP of G. So hopefully you should just be thinking, I mean, you can try to prove that this is a group action yourself, but you should be thinking this is well defined because GS G inverse should be another p-Sylow subgroup by the second theorem. We prove that this is a bijection to another p-Sylow subgroup, so this is okay. This is well defined. So what we want to so we get from this action by the p group fixed point theorem that the size of our set here is going to be equal to the size of the fixed points mod P. And this is just equal to NP. So in a sense, what we want to prove is that the fixed points only have one element, or in particular are 1 mod P, but we're going to prove that there's only one element. So let's just describe what these fixed points look like. So we see that we can describe the fixed points as so. So the fixed points of this action are going to equal those sets S, or should I say subgroups, in SP of G, such that GS G inverse equals S for all G in P. So it's just those elements where if I take any P group element, any element in my p-Sylow subgroup P, I'm going to just fix my other p-Sylow subgroup S. But we see this is equivalent. We've seen this GS G inverse before equals S. This implies that G is in the normalizer of S. That's exactly what that means. But if this is true for all G and P, this means that P is in the normalizer of S. Okay. So now we've proven something. So an element S is, or should I say the subgroup S is a fixed point if and only if P is contained within the normalizer of S. So now we want to prove what this implies. So let's assume, like let's take S to be within a fixed point. Okay, let's take some fixed point S. Well, then I get that S and P are subgroups of my normalizer here, the normalizer of S. In fact, they're both p-Sylow subgroups. They are both p-Sylow subgroups of the normalizer. This is just because the size of the normalizer has to, divide the size of the group, and it also has to have the size of S as a factor of it. So it has to equal p to the n times k or something. So clearly S and P are p-Sylow subgroups. So let's see what that implies. Well, by the second theorem, now that I have two p-Sylow subgroups, I can apply the second theorem. I get that there's some element, let's call it G, in the normalizer of S, such that these are conjugate. So I can write P as G S G inverse. This is exactly what the second theorem guarantees for us. But remember that if G is in the normalizer, then this is exactly S. That's what definitionally this means. So I get that S is equal to P. That means if you have any element that's a fixed point, it's got to be equal to P. So that this just proved to us that the fixed points are just equal to P. And note that P is definitely a fixed point, because if you multiply it by other elements of P, you're just going to get the same group back. So nothing changes. Thus, there's only one element in the fixed points. So the size of this set as P of G, or NP, is got to be equivalent to 1 mod P. Because the fixed points just have one element. So that got us the first step. Okay. For our second step, which is proving, just a quick reminder, we want to prove that the actual size can be determined by the normalizer, the index of it in G. This is equivalent to showing that there's a bijection between the set of p-Sylow subgroups and this normalizer. This is what essentially we want to show, that there's this bijection that exists between these two. Now I should note before doing this proof that even if we can describe NP to be equal to this, it unfortunately doesn't help us too much with the determining what it is in real world cases if we're trying to apply the Sylow theorems, because in practice it's not easy to know exactly what this normalizer is in general. It's very hard to determine unless you know something specific about the group. But usually when we're using the Sylow theorems, we do it to talk about groups in a more general sense. So proving things about all groups of order 20 or 30 or 60 or something. And in that case, it's hard to say anything general about this normalizer. Nonetheless, we can prove interesting things using this result. So hopefully this might remind you of the orbit stabilizer. May remind you of the orbit stabilizer theorem, which tells us that if our orbit is SP of G and our stabilizer is NG of P, the normalizer, then I'm going to get exactly this, which is there's a bijection between the orbit and G mod the stabilizer. So let's try to find a group action where this is the case. Okay, well, we have from the second theorem, from Sylow 2, I get that G can act on SP of G by G dotted with P equals GPG inverse, and this is transitive. This is transitive. That was one of our corollaries. Which means I'm going to just choose one p-Sylow subgroup, more specifically the one we described in the statement of the theorem. So choose P and SP of G. We get that the orbit of P is the entire set. Now this is helpful because, remember, in orbit stabilizer, we just have the orbit. We don't have the entire set. Here we can guarantee that the orbit is the entire set. So, G mod the stabilizer of P has a bijection to SP of G, which is the orbit of P, by orbit stabilizer. So really we're curious, what is the stabilizer of P? Well, if G is in the stabilizer of P, what do I get? Well, I get that G dot P, which equals GPG inverse, has to fix P, so it equals P. But this exactly means that G is in the normalizer. This is definitionally what that means. GPG inverse equals P. So G is in the normalizer of P. Which tells us exactly that I get that the stabilizer of P equals the normalizer G of P. If you're in the normalizer, you have to be a stabilizer. And if you're a stabilizer, you're in the normalizer. So they're equal to each other. Thus, by orbit stabilizer theorem, I get that G mod the normalizer of P has a bijection to the set of p-Sylow subgroups in G. In particular, the size of this equals NP, and the size of this is just the index. And the bijection means these sizes are equal to each other, which proves exactly what we wanted. Okay. So you know how I mentioned that in practice it's kind of hard to find exactly what this index is. So in practice it's hard to determine what MP is from this. Well, there are some tricks we can derive from this which make it easier for us to determine what MP is. And it helps us whittle down the possibilities. So here's a corollary. If the size of G equals p to the n times m, where p doesn't divide m, then we get that np has to divide m. So that tells us basically I only have a finite amount of possibilities for what np can be. If np has to divide m, this limits those possibilities. So let's prove this real quick. So let's just determine what m is. Well, m is going to be equal to the size of G divided by the size of some p-Sylow subgroup P. And we know we can rewrite this as like the index. That's just because if I divide by p to the n, I get m. So we see that n sub p, as we determined before, is the index of the normalizer. And now I can divide, I can multiply by 1 over p on the top and bottom here, just to rewrite this fraction. So nothing's changed. But now this top part here is m, and this bottom part here is the index of p within the normalizer of p. And recall that p is a subgroup of its own normalizer, so this index has to be an integer by Lagrange's theorem. So I get that m equals this index times NP. But as you can see, this necessarily implies that, well, NP has to divide M. Okay, great. Once I do the video on examples of using the p-Sylow, the Sylow theorems, this should hopefully make more sense why you would even want to ask this question, does NP divide M? It's a really good way of whittling down the possibilities for what NP can be, and can actually be a really great way of determining exactly what it is, with the fact that NP is 1 mod P. So using those two facts together really helps us whittle it down. And the second corollary here is going to help us answer why should we really even care about the size NP? Like, why should we care how many of them there are? Well, this corollary says if NP is just equal to 1, then if P is the p-Sylow subgroup in G, then I get that actually P is normal in G. Okay, let's prove this. Well, it's actually very quick. There's a way to prove it using the third and the second. We're going to prove it using Sylow 3, which is I get that NP is the index of the normalizer. And so if this equals 1, well then the normalizer has to be the entire group. But that definitionally means that P is normal in G. And if you want to think of this in terms of the second theorem, well, the second theorem tells me if P and Q are p-Sylow subgroups, then G, P, G inverse, there exists some G such that this equals Q. But recall, if there's only one p-Sylow subgroup, since NP is 1, then Q has to also equal P. Or I could write P as Q. Either way, I just get the GPG inverse equals P, which then implies that P is normal in G. Okay. So all of these together should give you a good idea of not only why we should study p-Sylow subgroups, but also some interesting properties about them. And hopefully next video, I'm going to give a bunch of really good examples on how to prove different things about general groups using these theorems. Thanks for watching.